The work-energy theorem. By the end of this lesson, we'll be able to describe the work done on an object or system by a given force or collection of forces. We'll be able to describe the behavior of a system using conservation of mechanical energy principles, while also describing how the selection of a system determines whether the energy of that system changes. Some important vocabulary before we get going. Work is the transformation of energy through the actions of a force acting for some displacement. Still using the unit joules. Dissipated energy is the energy lost to the environment or surroundings. System is the picture we care about. The work-energy theorem is the change in an object's kinetic energy is equal to the sum of the work being done by all the forces acting on that object. A force displacement graph, or F versus X, a graphical representation of how force varies with displacement in a system. Speaking of energy in a system, if a force that is not included in the system is acting on a system, this is an open system, which means energy can increase or decrease depending on what kind of work is being done on the system. We have a couple of different types of work. That is positive or negative. Positive work means a transformation of energy is taking place within a closed system, or if the system is open, the total mechanical energy increases. That means work is being done by an external force on the system. If work is negative, or when work is negative, energy is leaving the system. Remember that work equals force times displacement times cosine theta. Theta is the angle between the force vector and the displacement vector. If we look at an example where we have the weight force down and the normal force up, normal means perpendicular. And let's say we have a force acting up and to the right while friction is acting to the left. We can analyze the work done by each of these forces. Obviously, this object is sliding to the right. Could be speeding up or could be slowing down. We don't know the magnitude of F or the frictional force. So this object is sliding to the right because friction opposes sliding, which means that we're probably on a horizontal surface. Have to be on a horizontal surface. If we're on a horizontal surface, then the normal force is normal. It's directly up. Normal means perpendicular. So that angle between the normal force and the displacement, which is to the right, is 90 degrees. Cosine of that 90 degrees equals 0. So the normal force does no work, the weight force does no work, frictional force is going to be doing negative work, while F has a horizontal component and a vertical component. The vertical component is still acting perpendicular to the displacement, so the vertical component does no work, while the horizontal component of F is doing work in the same direction as displacement. In fact, if we consider that angle, and if we're in the same direction, if force is acting in the same direction as our displacement, then that means that angle between those two vectors is 0. Cosine of 0 is 1. So that would be the maximum work done by that force. Meanwhile, if the frictional force is acting in the opposite direction of displacement, then the angle between your displacement to the right and frictional force to the left is going to be 180 degrees. Cosine of 180 equals negative 1, which means we're going to be doing negative work. And if that angle is 90 degrees, as we've said, cosine of 90 is 0. So whenever we're dealing with a force that's perpendicular to the displacement, there's no work being done by that force. We just have to be careful of recognizing what our displacement is. And remember that if a force is acting at an angle, we can resolve it into its horizontal and vertical components and analyze each of those components separately. When an object is undergoing circular motion, it's important to figure out where the object is when we're calculating work. At each of these points, we have obviously a net force directed inwards, right? We may also have a force acting outwards. An example of this could be a roller coaster. And at the top of the loop on the roller coaster, we have a net force acting downwards, while
we still have some normal force. In this case, our centripetal force, which would be the force pointing in, the weight force, minus our normal force, would equal mass times our centripetal acceleration. This would be our total work done. We would analyze each of these forces to figure out the work done. So if we wanted to find the work done by the weight force, the work done by the weight force will be mg times the displacement times cosine of the angle between the two. For a roller coaster, our very next point of motion is going to be lower than where we were. So there is gravity doing work. We can usually simplify this and we can just say the work done by the normal force is going to be whatever that normal force equals times our displacement. So our total work would be work done by the weight force minus the work done by the normal force. And that gives us our net work. Meanwhile, if we take the situation where we have a mass on a string and it's going through a vertical loop, let's say. So now we have the weight force acting down and then the tension force pointed in. Now the weight force is the component of our total net force that is going to be doing work, while the tension force would do zero work because it's perpendicular to the direction. We have a tangential velocity in the same direction as our weight force in this instance. While we're here, F times displacement. If we were presented with a force versus displacement graph, we know that the area under this graph would have to represent the work being done, or the total change in energy, or the integral of force with respect to displacement. Displacement could be represented on the graph as d. It could also be represented as x. It could also be represented as y or r. Any of these. And we're still looking at the integral would represent the change in energy. Meanwhile, the slope would be f over x, let's say. Well, if we're dealing with a spring in some way, then this would be equal our spring constant. So our slope of force versus displacement could equal our spring constant.
So when do we use the work energy theorem? When we're trying to find the energy that's been dissipated, a certain force when there are multiple energies present. So if it feels like a conservation of energy situation, but there's a force thrown into the problem, remember your work energy theorem. It's going to get you out of a lot of odd situations. Work when given speed, height, and a spring. There's your multiple types of energy. Speed is kinetic energy, height is gravitational potential energy, and a spring or piece of elastic would be our elastic potential energy. So let's look at a worked example. I'll go through this, but I strongly encourage you to pause the video here and try it for yourself. An object of mass 10 kilograms starts from rest and is allowed to slide down a 5-meter long rough incline with a coefficient of friction μk equals 0.2 and at an angle of 30 degrees from the horizontal. How much work is done by gravity? So here we're going to be analyzing the different forces acting on the object. The first thing that I would do is I would draw this picture out. I would say here's our mass. And the length of the incline is 5 meters, and it's at some coefficient of friction. Gives us a coefficient of friction of 0.2. So we're going to draw a free body diagram. We have our weight force acting down. We have our normal force acting this way. We have our frictional force. We're sliding down the ramp, so our frictional force is going up the ramp. And we can, of course, continue on our normal force and resolve our weight force into vectors. Remember that this theta equals our original theta when we resolve the vector like this. How much work is done by gravity? Work equals force times displacement times the angle between the two. So we know that gravity acts down. When we're dealing with work, we can look at the parallel component of your force, which is going to be mg sine theta. That's the little piece of gravity, the fraction of gravity that's causing it to slide down the ramp to begin with. And then we can multiply that by our displacement. So if we have 10 times sine of 30, we have 50 times 5, which gives us work done, is going to be a positive 250 joules. Positive because the parallel component of your weight force is acting in the same direction as your displacement. Meanwhile, if we were looking at the frictional force, we would do the work done equals our frictional force times our displacement, and the angle between those two is going to be 180 degrees because frictional force is opposing the sliding. So to figure out this work, cosine of 180 is going to be -1. So frictional force is going to be mu times mg cosine theta times our displacement. And from there you can plug it in your calculator. You can also calculate your net work by adding up all of your work. So the work done by gravity, the work done by your frictional force, the work done by the normal force, which we know to be 0. That would give you your net work. From there you can figure out the change in energy, or the change in kinetic energy in this instance. Because the work done does equal F times d cosine theta, and it also equals our change in energy, the work energy theorem. Now it's your turn. Practice, try it for yourself, ask each other, ask me for help. Keep asking until you get it.